Hi, welcome to Electronic Communications. This short video is about electrical current. We're starting with electrical current because you've probably got some experience with the flow of water in rivers, and water's a good analogy for electricity, so that's why we're going to start with current. So in a river where there's a current, it's the water that's flowing, but what's flowing when we're talking about electrical circuits? So yeah, what's moving around the wire? Well, it's electrical charge that's moving in a wire. But what's electrical charge? You would have had some prior experience or knowledge of atomic structure. This slide shows the Bohr model of the atom. You can see that there's a nucleus that has positively charged protons, and it has neutrons which have no charge. And then in orbitals around the nucleus there are electrons, and these have a negative charge. So it's these negatively charged electrons that are the charges that flow in a wire. Most of the electrons flowing in a wire, most of the electrons don't move away from their nucleus. It's just these outer valence electrons, the ones in the very outermost shells, that are delocalized and can be made to flow through a wire. So this dude is Benjamin Franklin, and he, a couple of centuries ago, said that electrical charge can't be created or destroyed, but it can be transferred from one place to another as a current in a wire. Now, we know that we have something that we call static electricity, and that if we rub, say for example, a balloon on our hair, we can kind of charge those objects up. We can sort of transfer charge from the balloon to the hair or vice versa. Now, this slide shows some objects that have got charges in them. Now, the first object has the same number of positive as negative charges. So we would say that it's, even though it has charges, as an object overall, it's uncharged. This middle object has got more positive charges than negative charges, so we would say it's positively charged, and this object is negatively charged. So a deficit of electrons results in a positive charge, and a surplus of electrons results in a negative charge. This is very important. Charges that are opposite will attract each other, and like charges, or charges which are the same, will repel. So this shows two positive charges which, if brought together, would each experience a repulsive force pushing away from the other positive charge, and the same would happen if you had two negative charges being brought close together. The electrons in a metal, some of them, the valence electrons, those on in the outermost shells, are delocalized. So it means that they can be made to flow in a wire if they experience a force. When Benjamin Franklin started studying the flow of charge, he had no way of knowing whether or not the positive charges were moving in a wire or the negative charges. So they made a decision that it would be that it's the positive charges that move, and unfortunately got it wrong, as we now know that it's the electrons that move in a wire. And so the problem that this means is that charge really flows from negative to positive, okay, because the electrons are negatively charged, So they're going to want to migrate towards positive charges. So the flow in a wire is from negative to positive. But it's too late to change. So Benjamin Franklin assumed that the charges were positive. So when we draw circuit diagrams, we assume or consider that the charges that are moving in the circuit are positive and that they'll move from the positive terminal of the battery to the negative terminal. So how do we measure charge? Well, the elementary charge, which is the charge on one electron, is very, very, very small. There are billions of electrons transferred from a balloon when it's rubbed on someone's hair. So the standard unit of charge is called the coulomb, and 1 coulomb of charge is equivalent to this many electrons. It's a lot. Yeah, it's a lot. So current is the rate at which charge flows, and current is measured in amperes. So the quantity symbol for current is I, so we use this when we're writing equations involving current, and the unit is amperes, and so this is the symbol that we put after our answer. So expressed as an equation in words, current equals charge over time. So the current is the amount of charge that flows past a point in a certain time. And in symbols, I equals Q, I equals Q over T. Current equals charge over time. So we can rearrange that formula to make either I, Q, or T the subject, and it's important that you know how to do that. So here's our first example. So what current flows through a light globe if a charge of 30 coulomb flows in 10 seconds? And what would be the current if a charge of 30 coulombs flows in 1 minute? So the first thing that we need to do is we write down what we've been given. So we have been given that the charge is 30 coulombs and it flows in t equals 10 seconds, and we want to find out what the current is. So we use our formula, current equals charge over time, and we substitute in our values. 30 coulombs over 10 seconds. Okay, so that equals 3 amperes. If we want to know the current if a charge of 30 coulombs flows in 1 minute, then once again we write down charge 30 coulombs, but the time is 1 minute. Now a minute is not a standard unit, we need to convert that to seconds. Okay, so 1 minute is equal to 60 seconds. Now, current is charge over time, which equals 30 coulombs over 60 seconds, which equals 0.5 amperes. So we'll just do one more example to finish off this video. So in this one, a car headlight draws a current of 5 amperes. How much charge will have flowed through the headlight in 1 second and in 1 minute? So this is going to require us to rearrange our current formula. So we have a headlight drawing a current of 5 amperes. And we want to know how much charge will flow through the headlight in 1 second. So the time is 1 second.
Okay, and we want to know how much charge. So we use our formula that current is charge over time, and we need to rearrange it to make charge the subject. So if I multiply both sides by t, I get IT equals Q. So therefore I can say that Q is equal to the current, which is 5 amperes, times the time, which is 1 second, which is 5 coulombs.